Hi everyone, welcome to the beginning of our next unit of regular physics concepts. Here we're going to get into Newton's laws of motion, and in particular in this video we're going to discuss Newton's first law and Newton's third law. Since the second law is more mathematical in nature, and since this video is intended for non-AP physics classes, we're going to leave the second law for a later discussion. If this was an AP class, I would put the laws in order because the third law actually follows from the second law. So, first off, a couple of little cartoons about maybe Isaac Newton would have discovered gravity years earlier if William Tell had not wandered by to snag the apple as it was falling. And then a nice Far Side cartoon with a giant apple sitting over Isaac Newton's head. Now, these are referencing Newton's realization that there is a universal law of gravitation that both causes apples to fall from trees and causes our moon to orbit around Earth. But we're not actually going to discuss Newton's law of universal gravitation until the next unit. So for now, we're just going to be discussing Newton's three laws of motion. Now, if gravity is present, which will often be relevant in analysis of the second law, we will assume that it's going to be constant. And if it's on Earth, then that's the acceleration due to gravity of 9.8 meters per square second. Now, the three laws of motion are not really all Isaac Newton's original doing. In particular, the first law was from many centuries before. Even when Galileo realized it, it was already centuries old. But just putting Newton's first law in your own words, you can either do it as Calvin would do it, or you can actually be correct about it. So here are the three laws up front, and then we'll spend the rest of the video talking about the first law and the third law. The first law: objects maintain constant velocity unless acted upon by an unbalanced force. Now, a lot of people try to get away with thinking of demonstrations of the first law being like, oh yeah, an unbalanced force acts and then the object accelerates. The crux of the first law is different. The crux of the first law is simply that objects maintain constant velocity. That's their natural state of being. They maintain constant velocity. If they don't maintain constant velocity, then that means that something else has happened, which we call an unbalanced force. But the crux of Newton's first law, the whole point of it, is that the natural state of motion is for objects to maintain constant velocity. The second law is that when you do have unbalanced forces, then the net force acting on an object is equal to that object's mass times its acceleration. And again, we'll have more to say about this in a future video, a lot more. But I should note that it's actually a cause and effect relationship. The force is the cause, the acceleration is the effect. And for that reason, a lot of people state the second law as acceleration equals net force divided by mass. The third law is that every force results in an equal and opposite force. So we're going to come back to that later in this discussion in this particular video. So, as I mentioned before, the plan is going to be to discuss Newton's first and third laws today, leaving the more mathematical second law for the rest of our discussion in future videos. And after that, we'll spend the rest of the unit discussing Newton's second law and its applications. So, the first law by Galileo is that an object maintains constant velocity unless acted upon by an unbalanced force. Now, we need to discuss some vocabulary here. Constant velocity simply means constant speed and constant direction. Inertia. Newton's first law is often called the law of inertia, but inertia is simply a property describing an object's tendency to resist a change in its motion. In this course, we will be speaking mainly about translational motion, and therefore translational inertia. Well, that has a name. It's called mass. Mass is an object's resistance to a change in its translational motion. That is, back and forth, up and down, or side to side. Now, we can also analyze rotational motion in more detail than what we'll actually do later on in this course. But in so doing, we would introduce a different concept of inertia, often known as rotational inertia, but really called moment of inertia. But that's mainly something that we will leave off for an AP physics class. But mass, very important for us. Translational motion, that's going to be for this class. Now, with Newton's first law, keep in mind that people did not always think of this that way. Aristotle, back 2,300 years ago or so, more than that, he believed that objects naturally tend to come to a rest because it's in their nature to do so. His demonstration of this is the fact that a horse is required to keep a cart moving. Get rid of the horse and the cart will come to a rest. And of course that's because people back in Aristotle's time didn't quite understand the concept of friction, which is a force that tends to oppose motion, especially when you're talking about motion across a surface. That simply wasn't understood very well during the time of Aristotle. Now keep in mind, I'm not ragging on Aristotle. Aristotle was a genius. He came up with multiple ways of demonstrating that Earth is spherical. He even considered the possibility that Earth goes around the sun, but he rejected the possibility because it leads to the hypothesis that you should be able to observe certain stars moving throughout the sky during the course of a year as Earth's perspective on them changes. And that lack of observation demonstrated to him that Earth must not be moving. But of course, nowadays we realize that the stars are so far away that that's not measurable, but, I mean, they didn't realize that back in Aristotle's time. I mean, we have over 2,300 years of additional increasingly precise observations, understandings, theoretical understandings, and just general philosophical advice that Aristotle did not have during his time. So, by Isaac Newton's time, and even by Galileo's time, friction was well understood. So the idea is that objects maintain constant velocity. Even during the time of Niccolò Oresme, back around 1360, he noted that if you are on a ship that is moving out of a harbor at a constant speed, there is no way of telling whether it's the ship that's moving or whether it's the harbor that's moving in the opposite direction. There's just no way of performing any experiment one way or the other to say this. So that became known as Galileo's law of inertia, which I'll kind of go back here. So we often call it Galileo's law of inertia, but it really turns into Newton's first law. And this particular principle was so fundamental and foundational in the laws of physics that a slightly restated version of this eventually became known as Einstein's first postulate of relativity. So there you go. Half of relativity, in a manner of speaking, goes all the way back to the 14th century. Okay, what about car safety? The seatbelt in a car can be thought of as an inertia restraining device. In other words, during a collision, there's a very rapid acceleration in the car, and thus that could potentially lead to a very strong force acting on the car's occupants. Now, the seatbelt is able to stretch a little bit and allow you to remain safe during such a collision. At least safer than you would be if you were not wearing the seatbelt. However, you need to make sure that you're wearing your seatbelt correctly. Now, I'm not going to show the video here, but you can go to this YouTube clip to see a video of what happens when you don't wear a seatbelt during a rollover collision in a car. Now, making sure that you're wearing it properly means that you are maintaining about the right distance from the steering wheel. Here you can see the seatbelt here. This is not me. This is actually a picture of my original kind of physics mentor, Tony Wayne, wearing a seatbelt properly and about the right distance from the car steering wheel. That's known as the rattle distance. Now, you don't want to be too close. One, you can go directly into the steering wheel before the seatbelt stretches enough. Two, the airbag will come right out at you and potentially cause a much more significant injury than if you were wearing it properly. You also don't want to be too far back, like this, because in this case, with this increasing rattle distance, notice that in this case your center of mass is below the seatbelt, especially at that angle. It's kind of outside of the seatbelt. So as a result of this, during a collision, you could potentially end up sliding under the seatbelt and even getting decapitated. So make sure that you're wearing your seatbelt correctly. In other words, not like this, like this. With the right rattle distance, you're upright, and everything will be better in a collision than it would otherwise be. of course, hopefully you drive real safely, and also hopefully the people around you do as well, and you don't get into collisions. Now, in my actual class, I show a number of videos demonstrating Newton's first law in action. And the whole point of these is that in various situations where somebody is holding on to something, maybe not so securely, or part of something that suddenly changes velocity, that person will continue going at constant velocity. So if you're on a speeding boat that suddenly swerves in the lake and you're not buckled in, which you probably aren't on a typical boat, then your body will go flying out so that it's maintaining constant velocity, which means that it is changing its position relative to the boat, because the boat is what suddenly had a change in velocity. During a car collision, well, let's say that you're at a stoplight, somebody comes behind you, not noticing the stoplight because they're fiddling around with their stupid cell phone, and they end up hitting you. Well, suddenly your car's velocity changes from 0 to something that's non-zero in the forward direction. But your head, which might not necessarily be up against the headrest, will want to maintain constant velocity, in this case being at rest. So the car will go forward, your head will snap backward. That's the origin of whiplash. Or, in this situation, you suddenly hit the brakes and something is not very well secured. Well, that thing is going to keep going forward at constant velocity. So, remember what constant velocity means? Again, it means not just constant speed, but also a constant direction. So, if you suddenly turn around go around a curve really fast in a car, and if there isn't enough friction force to allow you to do that, then your car naturally wants to maintain constant velocity, which means going straight, which would mean swerving off the road. And if you're going too fast, the friction force will not be enough to allow you to do that. We'll have more to say about that in the circular motion unit. But yeah, objects naturally maintain constant velocity. That is the crux of Newton's first law. What about Newton's third law? So again, we're skipping over the second law for now, the idea that when there is an unbalanced force, the force acting on an object is equal to mass times acceleration. So Newton's first law, objects maintain constant velocity unless acted upon by an unbalanced force. The second law, when there is an unbalanced force acting, that's equal to the mass of the object times its acceleration. The third law, when there is any force acting on an object, that results in an equal and opposite force. And for every force acting on the object, there is an equal and opposite force. So if there are 5 different forces acting on an object, then there are going to be 5 different what we call action-reaction pairs. So the action-reaction pair, the reactive force, is going to be acting on the agent bringing about the force. So let's say your butt is exerting a force downward on the chair. Well, the reaction force is your chair exerting a force upward on your butt. Or if you're standing motionless while wearing ice skates in a skating rink and you roll a bowling ball across the floor or throw it, well, you're going to exert a force on the ball, which is going to send it forward, but the ball is going to exert a force on you, sending you backward. Or in a car collision, if there is a collision between, say, a Ford F-350 and a stupid car, also called a smart car, but it's a stupid car for reasons that will become clear very soon, both objects actually feel the same force. The Ford F-350 feels the same force as the stupid car, but the stupid car has a much smaller mass, Newton's second law, which we'll have more to say about later on, and as a result undergoes a much greater acceleration during that collision. Same thing happens with the bowling ball. So as a result of undergoing a much greater acceleration, that means that the occupants of the stupid car will feel a much stronger force, and they will be much more likely to suffer a very serious injury as a result of that collision. Stupid cars are not safe vehicles on the roads. Now, what about Moon in orbit around Earth? Well, our Moon orbits Earth due to the gravitational interaction between Earth and Moon. That means that there's going to be an equal force on Earth as there is on the moon. But Earth is 80 times as massive as the moon. So our moon is going to experience an acceleration that's 80 times larger than Earth. That's why we generally say that the moon is orbiting around Earth, even though what's actually going on is they're both orbiting around the common center of mass. But since Earth is 80 times more massive, we don't really think of that as all that much of a motion, because our motion around that center of mass is very tiny compared with that of our moon. In fact, that center of mass is actually inside of Earth. It's something like 3/4 of the way from the center to the surface, on average. Now, solar sails are these large, thin, reflective sails that reflect sunlight. And the idea with these is that by reflecting sunlight, in order to reflect sunlight, you have to exert a force on the photons, the particles of light. And since the solar sail exerts a force on the photons, that means the photons are exerting a force on the solar sail, Newton's third law. What's the result? The solar sail accelerates. And it accelerates in the direction opposite to the direction that the sunlight is coming from. This technology has been successfully tested in the Icaros spacecraft. It's not the main way that it moves. It's just that they unfurled these solar sails to give a test of this to see that it actually works during the spacecraft's mission to Venus. Now, one of the ideas of this is that very tiny spacecraft could potentially use solar sail technology to accelerate a lot more quickly and visit other solar systems, like, say, the Alpha Centauri system, which is the closest star system to our Sun. In fact, it has one star, Proxima Centauri, which is the closest star to our Sun. It's about 4.25 light years away. And Proxima Centauri actually has a planet orbiting around it in the habitable zone, which means that if conditions are relatively reasonable, in other words, if the planet has a decent atmosphere, then you should expect that liquid water would exist in a stable form on the planet's surface. So it could potentially be an abode of life. Now, just because it's in the habitable zone doesn't mean that it's habitable, and just because it's like that doesn't mean that liquid water is stable on the surface. For example, Mars is barely in our solar system's habitable zone, but liquid water is not stable on its surface because Mars hardly has any atmosphere at all. But nonetheless, it leads to very exciting possibilities for exploration, and the solar sail technology is one possible way of doing this. So for large solar sails, there would be a continuous but relatively small acceleration, but the point is the acceleration would be continuous, and since there's practically zero friction in the interstellar environment, once the solar sail obtains a pretty high velocity, it's really just going to keep going. Newton's first law. It's going to keep going toward its target. So again, you could potentially explore other planets, especially around some of the nearby star systems. This might not happen within our lifetimes, but it's something that could be done over a number of generations and kept track. Rockets also work by Newton's third law. So there's a very powerful chemical reaction in the rocket fuel that produces a lot of energy, and much of that energy is used to simply expel the gas out the exhaust. Well, why do we want to do that? Well, that energy used in expelling the gas out of the exhaust produces a large force on the gas, the spent rocket fuel. And action-reaction pair, the spent rocket fuel exerts a force back on the rocket. In other words, rockets do not accelerate by exerting a force against the ground. They don't accelerate by exerting a force against the air. They accelerate by exerting a force against the spent rocket fuel, which thereby produces a reaction force on the rocket itself. So, for example, in this case of the space shuttle, notice there is a whole lot of spent rocket fuel here that is going into, and a lot of energy being produced as a result, and that action-reaction pair exerts a force back upward on the rockets carrying the space shuttle. Same idea is used in retro rockets. So, for example, the Phoenix lander, which landed on Mars in 2008, used a series of retro rockets to allow itself to land on the surface of Mars. So as it got, it first used a parachute to slow its velocity once it was released from the spacecraft that carried it. But as I mentioned, Mars doesn't really have all that much of an atmosphere. The atmospheric pressure there is similar to what it is at 110,000 feet on Earth, above Earth's surface. So not very much air there. So it's not going to slow it down enough to prevent a lot of damage on impacting the ground. So instead, it eventually jettisons the parachute and turns on the retro thrusters, and those are what end up slowing the spacecraft down as it eventually reaches the surface. In fact, they went one step further than this with the Curiosity rover that has been exploring large areas or a large region of the surface since I think 2013, where it kind of stayed above the ground, and then it used a screw mechanism to unscrew a platform that very slowly lowered the rover to the surface, because it's a very complex, very delicate craft, so they needed to be really careful with that one. So I'll try to remember to post a link of this video showing an animation of the European Space Agency's, ESA's, Schiaparelli lander in its descent to the surface of Mars. And in that you will notice examples of how all three of Newton's laws are demonstrated. So this is the end of our discussion of Newton's first law and Newton's third law. The rest of this unit will focus on Newton's second law, its calculations, and its applications. So I'll hope to see you all then, and thank you for watching.